Hello, Calculus. Today we're going to look at infinite limits and limits to infinity. And the goal for today is to be able to evaluate limits at asymptotes, as well as evaluate limits where x approaches infinity or negative infinity. So the plan for this video I'd like you to do is just pause it when you need to, and then copy down the examples and copy down the work, and then play the video at whatever speed is appropriate for you. And then play whenever needed. So in class, you'll be able to use these examples and use these notes to answer questions, and then you'll have the benefit of asking your peers as well as me if you get stuck on something. And if there's anything in this that doesn't make sense to you, please bring it up to me in class, because I do want to make sure that we iron out the details. I might misspeak, or if I make a mistake, point it out to me just in case I missed that. But anyways, so let's begin. For talking about limits at asymptotes, if you look at the function 7 divided by x minus 5, and I asked you about the limit as x approaches 5, if we tried to evaluate, if we plug in 5 into that, I would get 7 over 5 minus 5, which is 7 over 0. So graphically, that means we have a vertical asymptote. At x equals 5. And what does that mean about the limit? The limit does not exist. It fails to exist. It doesn't approach a finite real number. But at asymptotes, there's three things that could happen. At an asymptote, from both sides of the limit, it can be going to infinity, it can be going to negative infinity, or one side of the limit can be going to negative infinity, where the other side of the limit can be going to positive infinity. So in those situations, although the limit does not exist in any of these situations, if the limit's going to positive infinity on both sides of the asymptote, then we're going to say that the limit of the function as x approaches that value is infinity. If on both sides of the limit are going to negative infinity, then again, the limit doesn't exist, but we're going to say that the function is approaching negative infinity as our x values approach, in this case, is 0. However, if on both sides of the limit are going to different infinities, then we'll say the limit does not exist. So that's it for limits at vertical asymptotes. But then the question is, how can we figure this out without a graph? So how do we evaluate without a graph? What we're going to do is we're going to plug in a number really close to the left and to the right of the limit. We don't need the exact number, but I just need a sign. And I'll explain why in a second. In this situation, I want to find out what case is happening here at 5. So we know we have a vertical asymptote. But I want to know if the function is going to infinity on both sides, or negative infinity on both sides of the asymptote, or one's going to positive, one's going to negative. So that's what we're going to test here. And so what I'm going to do is I'm just going to plug in a number really close to 5, and this is saying the limit as the function approaches 5 from the right. And so I want to find out from the right, is it going to positive infinity or is it going to negative infinity? That's what we're going to find out. So just plug in a number slightly bigger than 5. And again, I know if I plug in numbers really close to 5, I'm going to get either positive, really big numbers, or really small numbers. So it's going to positive or negative infinity. I just want to know whether it's positive or negative. So if I plug in a number just bigger than 5, I'm going to use 5.01 minus 5. The numerator, no matter what, is going to be a positive number. And the denominator, if I take something just bigger than 5 and subtract 5 from it, the denominator is still going to be a positive number. So if I take a positive divided by a positive, I know my output's going to be positive. And since we know it's going to infinity, then the limit as the function approaches 5 from the right, it's going to infinity. So we know from the right, this is what the function's doing. Now, if I want to find out what's going on to the left side of the limit, so this is the right side of 5, this is on the left, then we're going to plug in a number just smaller than 5. So think 4.09, let's say. Now, the numerator is going to stay positive, just a 7. If you subtract 5 from excuse me, I should use 4.99, not 4.09. If I subtract 5 from 4.99, that's really close to 5, but the bottom is going to be a negative value. And if I do a positive divided by a negative, then we're going to go to a negative value, and we know it's going to infinity. So that means as x approaches 5 from the left, the function's approaching negative infinity. So if we go back to our original limit here, what's the limit of the function as x approaches 5? Well, one end is going to infinity, one end is going to negative infinity. So we're just going to say the limit does not exist. And that's it. It's not going to infinity or negative infinity. One's going to one infinity, one's going to the other. So we're just going to D and E that one. Now, in this example, we're going to do the same process. What's happening to the function as x approaches 0? We know that if I plug in 0, I get 5 plus 0 over 0 squared, which is 5 divided by 0. So that implies that we have another vertical asymptote. So at 0, we have an asymptote. The question is it going to positive infinity or negative infinity? So we're going to look at the limit from the left and from the right. So the limit of this function as x approaches 0 from the right, let's just plug in a number just bigger than 0, like 0.01. If I square that, a positive plus a positive is certainly going to be a positive, and any number squared is going to be a positive, and a positive divided by a positive is going to give us a positive value. And I know the closer I plug in numbers to 0, the closer this thing is going to go to infinity. So from the right, as the function approaches 0, it's going to positive infinity. What about the left? So if I take the limit of 5 plus x over x squared as x approaches 0 from the left now, we're going to look at a number just smaller than 0. So I'm going to use 5 plus, let's use negative 0.01 over negative 0.01 squared. Now 5 plus negative 0.01 is still going to be a positive number. And a negative number squared is still going to be positive. And when we do a positive divided by a positive, we're still going to get a positive output. So it's going to approach positive infinity from the left as well as the right. So if I said, what's the limit of this function as x approaches 0? It's going to be positive infinity. All right. And so that's it for limits at asymptotes. In terms of limits at infinity, this is something that we've done before. We just called it end behavior. So what's the function doing as you go to negative infinity and positive infinity? And so if we look at this green function here, as this function goes to negative infinity, the limit is approaching this horizontal line, and it looks like it's y equals negative 1. If you look at the function as x approaches positive infinity, it's getting very, very close to this orange horizontal line, which is positive 1. And so quickly we can see what the function is doing if there's a horizontal asymptote. So that's it for as limits approach infinity. We'll look at some functions and see how to tell the difference in a second. So evaluating limits at infinity analytically can be a little weird. Anytime you get a function where as x goes to infinity, you have an infinity divided by infinity case or infinity minus infinity case, we don't know what that is. Infinity divided by infinity, is that 1? Is it 0? Is it negative 3? Same thing with infinity minus infinity. All of these are indeterminate forms. We do not know what they are until we do a little bit more work. So we have to find some other strategies. And luckily, one of them we've already used before. So one strategy is when we're given rational functions, we found horizontal asymptotes. So again, we look at the degree on the top and the degree on the bottom. If the degree on the top is bigger, then there was no horizontal asymptote. That means that function is going to infinity. Now it's either positive or negative infinity. We don't know which one. We'll have to do a little bit of work. If the degree on the top and bottom are the same, then it's the ratio of the leading coefficients. However, it's positive or negative. We don't necessarily know if it's going to be a negative of the ratio of the leading coefficients or positive. So we'll do a little bit of work to check that out. And lastly, if the degree on the top is smaller than the degree on the bottom, then the denominator is going to go to infinity much faster than the top. And when you have an infinitely big denominator, your value is going to get infinitely close to 0. So the limit will be 0. No positive or negatives, just 0. So here's the function 2x plus 1 divided by x minus 1. What does this function do as x approaches infinity? Well, the degree on the top and bottom are the same. So it's just going to be the ratio of the coefficients, 2 and 1. Now as x goes to positive infinity, 2 times infinity plus 1 is going to give you a positive output. Again, a really big number minus 1 is still going to be a positive number. So we're going to go to positive 2. In this example, the limit as this goes to negative infinity, well, again, the degree on top and bottom are the same, so it's going to be the ratio of the coefficients. And as x goes to negative infinity, 2 times, think of it as negative infinity plus 1 is going to be a negative infinity value. And as x goes to negative infinity minus 1 is also going to be a negative infinity value. And the double negative cancels, is going to create a positive value. So it does also become 2. Now if I look at this one on the bottom, the degree on the bottom is bigger. So as x goes to infinity, if the degree on the bottom is bigger, it's going to go to 0. Now, when x goes to negative infinity, it's the same thing, whether it's positive or negative infinity. If the degree on the bottom is bigger than the degree on the top, that limit's just going to go to 0. Now, these last 2 cases are infinity minus infinity cases. As x goes to infinity, infinity to the third power times 3 is going to be infinity, and 11 times infinity is also going to be infinity. But you can tell that something to the third power is going to go to infinity a lot faster than something to the first power. So this first term is going to be way bigger than the second term as we go to infinity. In fact, infinitely bigger. And so this thing is just going to go to infinity. One way to do it without just by looking at it, we can do a little bit of algebra to it to double check that. If I factor out the x, and then this becomes 3x squared minus 11, then as x goes to infinity, you have an infinity here. Infinity squared times 3 minus 11 is also infinity. And infinity times infinity does imply infinity. It's not a indeterminate form. It truly is going to just go to infinity. So that function, as x approaches infinity, shoots up to infinity with it. As x goes to negative infinity, not much is really going to change here. This first term is still going to beat out the second term. And if you put a negative infinity here, a negative number cubed is still negative. A negative infinity, you're going to have a double negative here, so you're going to have a negative infinity plus infinity. But again, this infinity is going to get infinitely bigger faster than this one is, so that's going to it's going to outbeat the first one. The first one's going to outbeat the second one, and we're going to go to negative infinity. And again, if we did the same thing where we factored out the x, as x goes to infinity, this first one, negative infinity, then we're going to have a negative infinity case here. Anything squared is going to be positive. So this is going to go to a positive infinity. And a negative times a positive will still give you that negative. So a little bit of hand waving, because infinity is not a value, but it's more of an idea. But that's what the function is approaching as we go to an infinitely big negative number. So some examples of square roots. The process is really the same. You just have to, I almost call it fake algebra. As x goes to infinity, adding 2 or subtracting 3 doesn't do anything to the output. It's going to infinity. Those are meaningless values. So what's really happening here is the battle between the leading coefficients. And so in this case, as x goes to infinity, this is approaching, we're going to look at the ratio of the leading coefficients. Now the leading coefficient of the top is the square root of 1. The leading coefficient on the bottom is the square root of 4. So that's actually going to approach 1/2, not 1/4. So just be careful for that when we have the square root. As x goes to negative infinity, does that change? Well, the degree on the top and bottom are still the same. The degree on the top and bottom are effectively 1, because when you take the square root of a squared number, you're going to get the square and the square root cancel out and just get it to the first power. So we're still looking at something of the ratio of the leading coefficients. And because even if it's a negative number and we square it, the output will be positive. And that's true for the bottom too. So we're still going to get a positive 1/2 as our limit. If we look at this one, the degree on the top and bottom actually are the same. Again, as x goes to infinity, the -5 doesn't really change anything. The 9x squared, the square root of that, excuse me, as x goes to infinity, grows at the rate of 3x. And again, we can just take the ratio of the leading coefficients. The top coefficient is 3. The bottom one is the square root of 9, which is 3. and 3 over 3 is 1. As x goes to negative infinity, how does this work? Well, this top here is going to go to a, if you think of 3 times a negative infinity times minus 5, that's going to go to a negative value. So this top is going to approaching negative infinity. This bottom, if you square the negative infinity, it's going to become positive, and then multiply it by 9, add 1, and square root it, that's going to go to a positive infinity. So here, although it's the ratio of the coefficients, 3 and square root of 9, the top is going to go to negative infinity, the bottom is going to go to positive infinity, and we're actually going to get a negative 3 over 3, which is negative 1. So that's what I mean by we got to be careful. It's the ratio of the leading coefficients, but is it going to positive or negative that ratio? Just think what happens if I plug in really big negative numbers. Is this thing going to give me a positive output or a negative output? In this last example here, the limit of x squared minus the square root of x to the fourth minus 3 as x goes to infinity. What happens to this function as x gets really big? Well, if you put infinity into infinity squared, that's infinity. Infinity to the fourth minus 3, the square root of that's also infinity. So this infinity minus infinity case is just another one of those indeterminate forms. And so what's going to actually happen here is I'm going to rewrite it and multiply by the conjugate. So I'm going to see if multiplying by the conjugate gets rid of the square root and allows me to look at it, look at a different version of this expression. If maybe this other look will give me a better idea of what this thing's doing as x goes to infinity. So I'm just going to write this as over 1, and then I'm going to multiply the top and bottom by the conjugate. So again, when we did this, the outer terms, x squared times x squared is x to the fourth. The inner and outer, the outer and inner terms cancel out, and then the only other term that gets left out is the last term. We have a negative times a positive, it's going to be negative, and when you multiply the same numbers, we're going to have this value squared. The square cancels out with the square root, so we just get x to the fourth minus 3. The denominator is just 1 times the x squared plus the square root of x to the fourth minus 3. And we're still taking the limit as x approaches infinity. Now what happens here is this negative is going to distribute into that parenthesis. So this is going to be equivalent to the limit as x approaches infinity of x to the fourth minus x to the fourth plus 3 over x squared plus x to the fourth minus 3. And yeah, these x to the fourth cancel out. So now we have this new way of looking at that function. 3 divided by x squared plus the square root of x to the fourth minus 3. And now here we see the degree on the bottom is way bigger than the degree on the top. The degree on the top is 0, the degree on the bottom is 2. So this thing is going to go to 0 because the degree on the bottom is bigger. And that's it. So again, just having these examples, if you're confused, please ask questions in class, and it's just something good to refer to, and in class you'll have a full block to kind of practice applying these skills. If you like the video and want to see more, consider subscribing, ring the bell for notifications, and smash the like button. If you have any questions, I'd love to hear it in the comments. And this video was brought to you by Raid Shadow Legends. Play today.